All right, so let's get started. Yeah, thanks for the kind introduction. Hi, everyone. I'm Albert. I'm a fifth-year PhD student with Professor Karen Liu, and today I'll talk about learning physics-based models to learn generalizable robotic manipulation. And so I'll try to answer 3 questions today. All right, yeah. So first, what is missing in robotic manipulation? And what causes this deficiency? And lastly, how can physics-based models help us in this regard? And so I'll start with answering what is missing in robotic manipulation today. Sorry, I think my computer just hanged. A second. All right, yeah, sorry about the hiccup. And so just to quickly reiterate, I'll try to answer these 3 questions today regarding robotic manipulation. And so I'll start with the first one. What is missing in robotic manipulation today? And in the past few years, we've seen a lot of very impressive robotic manipulation demos, many of which originate from the robot learning community. And robots are able to achieve very crazy demos and tasks that one can only dream about 10 years ago. And so this begs the question, has robotic manipulation been solved? And do we need to do anything besides just getting more data and scaling our models? And my answer is no. And despite the community's strong push on getting more data to train on bigger and bigger models, we're still far from solving robotic manipulation today. The policies that we get from learning methods are not generalizable nor robust. And the state-of-the-art algorithms, such as diffusion policy and reinforcement learning, are not able to tackle these challenges. And so diffusion policy, as an example, the first video I showed, it's relatively stable to train, and it can learn very multimodal actions. But they have, as we all know, it's limited in generalizability, and it's sensitive to the demonstration data set size. And so in the video I showed, probably one would have to retrain the policy for each of the shapes you're trying to manipulate. And then the other big algorithm, reinforcement learning, is it can learn very sophisticated emergent behaviors and has more robustness in execution. But to train a policy, it tends to be a very expensive and tedious tuning process, and the learned policy is task-specific. And so in the second video I show, they are only able to do the task on one object and one environment. And so we should then ponder the question, what causes this deficiency? Why is manipulation difficult? And the key lies in the rich physical constraints that govern manipulation, which arguably exceeds the complexity of any other robotic applications. And some of the notable ones that I'll cover today include collision and robot reachability constraints, contact modes, force closure, and friction cone. And the existence of these constraints make learning manipulation exceedingly difficult, as the motion must adhere to these constraints. And breaking these constraints will lead to failed execution, and the task will not work. And so diving into the three constraints that we have, the first one, collision and robot reachability. So this falls in the category of kinematics, and these are mostly geometric constraints. So they depend on the shape of the object we're trying to manipulate and the scene that we're manipulating in. And these are highly non-convex constraints, as we know from kinematic solves. It is possible to get a local solution when we try to enforce these, but it is very difficult to get a global solution. So the second category of constraint I'll talk about is contact mode. And this describes the contact configuration between the robot, the object, and the scene. So contact mode directly impacts the system's dynamics due to what's called hybrid dynamics in the literature. So if you imagine the example on the upper right corner, if there's no environment contact, we can never get the contact force with, say, this wall in the environment. Whereas if there is contact, which is a different dynamic mode, then we are able to get the contact force. And this is also largely geometric. Again, it very much depends on the shape of the object and the shape of the environment. And it is possible to detect and enforce these constraints, whether with tactile force sensing, and then there are classical control tools such as compliant or force control that will allow us to use these. But they're generally rather difficult to work with. And then the last type of constraint I'd like to talk about is force closure and friction cone. These mostly concern robotic grasping. And force closure describes, well, in a nutshell, like the sum of external forces and torques equal to 0. So that's required when we want to hold an object. And then there's also like a slightly more advanced inclusion where we try to reject any possible disturbances on the object. And then for friction cone, typically we use Coulomb friction model in literature. And both of these are conditioned on the contact point. So the force closure friction cone condition depends on how we decide to make contact with the object. And there are rich computational tools, such as formulating things as a quadratic optimization and whatnot, that allows us to leverage these constraints. And so what are some common attributes of these? So all these three types of constraints are non-convex, but mostly differentiable. We can either they're directly differentiable or they can be the subgradient can be obtained through smoothing. And because of the non-convexity, they are pretty computationally expensive to work with. Again, we won't be able to get a global solution if we want to just simply solve an optimization with these constraints. And they're extensively covered by past literature, the literature that predates robot learning. There's a lot of work on kinematics, dynamics, and there are also classical control theory tools that allow us to use these physical constraints. And then lastly, and most importantly, they all stem from physics, and in particular, mostly from classical mechanics and like kinematics and dynamics. So we can model these constraints reasonably well. And so that brings us to the third question. How can we leverage physics-based model to overcome the challenges in robotic manipulation? So at a high level, I will present a few ways to combine these to bake physics-based models into robot learning. And the first one is to move expensive analytical computations offline. And again, recall that a lot of these constraints are non-convex. So we can try to move that computation before we execute the task. And by, say, generating data sets or creating heuristic, or trying to learn a heuristic from the offline generated data. And then the second one, again, tying to the non-convexity, is that we can try to solve these problems with learning. So that can come in two ways. First, we try to learn an initial guess so that we see the non-convex solve better. Or we can use a different way where we try to refine a network output with these constraints and essentially solve a local problem. And so in this talk, I'll present three challenging manipulation tasks and covering dexterous grasping, dexterous pregrasping, and extrinsic manipulation. And I will show how using these physical constraints can help us achieve these manipulation objectives more efficiently. And so we'll start off with dexterous grasping. So what is dexterous grasping? This refers to grasping an object using a multi-fingered hand. And why is it difficult? A dexterous multi-fingered hand has way higher degrees of freedom compared to a parallel gripper. So we're looking at over 20 degrees of freedom for a fully actuated four-finger hand versus approximately 7 degrees of freedom for a parallel gripper. And there are a lot more constraints that occur in dexterous grasping. Collision, reachability, force closure, friction cone, they all show up. And in particular, force closure and friction cone do not come for free in dexterous hands, whereas they're pretty trivial in parallel gripper because if you have two grippers just closing in on each other, then you kind of get force closure and friction cone for free. And dexterous grasping is a very powerful tool for grasping objects because if we do it right, we can grab a wide range of different objects. So imagine how a human would use the 5 fingers to pick up things in the real world. And we can also provide very diverse grasping strategies, like say one can grasp an object from the top, from the side, and from many other different configurations. And so in this work, we propose a pipeline to generate dexterous grasping by combining learning and optimization. So in particular, we started off with building a grasp data set with analytical model. Again, this is an expensive process, but it is done offline. And then we can train a generative grasp point predictor, so in particular, a conditional variational autoencoder using this data set that we built. So if we look at the figure up here, so let's say we're given an object. We can train this model to predict where we should place the fingers. Like for example, the red, green, and blue points here. And then what happens if the prediction does not actually satisfy the physical constraints? So now we can actually solve a local optimization problem, assuming that the network gives us a reasonable initial guess. So we can massage the location of the grasp point if we compare the left side and right side so that it satisfies the collision, robot reachability, and force closure and friction cone constraints. So on the left side, we can see that the best contact force we can achieve is the three forces here, which clearly do not sum to 0, because I think it ends up with a net force this direction. Whereas once we solve this local optimization, we can apply contact forces that will result in a 0 external wrench on the object. And thereby, we can successfully grasp the object. And how well does this work in practice? So we put this on the robot, and we achieve nearly 90% success rate over 20 objects and 120 trials. And these objects range from objects that we gave during training and things that have never been seen before or similar shape, everything in between. And in particular, I would like to note that in our pipeline, because we have a generative model, we're able to grasp in a lot of different configurations, even for the same objects. And the robot can use multimodal strategies to ultimately pick up the object. Yeah, and there's also like certain objects that we tried that clearly cannot be picked up with a parallel gripper, but with a dexterous hand and with a good enough grasp generation pipeline, we're able to pick them up no problem. Okay, so the takeaway of this dexterous grasping task is that we at a high level, we can generate a grasp data set with physics, learn a grasp predictor, and then refine the prediction with this optimization that we formulate. And in particular, that considers the friction cone and force closure. And then finally, we can also use kinematics to solve for the hand collision for this, I believe it's 22 degrees of freedom problem. And so moving on to the second task, dexterous pre-grasping. So what is pre-grasping, and why does it matter? So in the real world, so previously in the grasping case, we assume that the object is sitting out in the open. But this is often not the case in the real world. The object that we want to pick up might be occluded and thereby ungraspable. And we need to move the target object in certain ways before we are able to reach a graspable pose and then establish a grasp or rigid linkage to the object with the robot. And note that this is made possible by the use of a dexterous hand because there's a lot more freedom in how we can interact with the object. And so why is this difficult? First of all, identifying a good pre-grasp is very challenging because a good pre-grasp is only defined by how good the grasp it can lead to. And this is a very computationally expensive query. And then computing a pre-grasp itself is also very, very expensive because how should we move the fingers around? How should we contact the objects to achieve this pre-grasp? And of course, there's a lot of possible collisions given that the object is in a lot of clutter and so on and so forth. And so our insight is that we need only at least one environment contact during a pre-grasp, and we only need 2 fingers to establish this grasp. So these observations allow us to reduce the search space and use model-based method. So we propose this pipeline where we do an offline training, construct a contact state graph, do a trajectory optimization, and synthesize hand motion. And I'll cover this in detail. And so first, the offline training. So again, defining a good pre-grasp is difficult, but defining a good grasp is relatively easy as we did in the first task. So we can learn a grasp generator, and we condition this, again, based on the observation that in a pre-grasp, we need at most 2 fingers. So we learn a grasp generator, so we complete the rest of the finger given 2 of the contacts. And then we can also learn a score function and like a heuristic to decide, hey, is this pre-grasp good or not? So this offloads the expensive computation to offline. And then now we can plan a contact transition with contact state graph. So what this means is that we build this graph based on where the fingers are placed on the object surface. So these forms the nodes. And then based on how we can transition between them, we create the edges. And then And then we can also train this a scoring function, which I think was shown earlier here, that will tell us whether this contact is a good configuration or not. And so now we have this graph. We can perform essentially a trajectory optimization problem conditioned on selecting one of the paths on the graph. And so intuitively what this means is that like we select where the fingers should largely contact, and then we kind of massage it around, decide what is the best trajectory to take. And then that gives us a physics realistic trajectory where, as shown here, we can see that we place two fingers, pivot the plate, and then put the rest of the fingers onto the plate. And so lastly, we can just, now that we have the fingertip contact locations, we can just synthesize the full hand motion with kinematics. And that looks like this. And so we tried this on a lot of environments where we can't directly establish a grasp. And our pipeline is able to achieve efficient pre-grasp planning. And so you can see that these are physics realistic, and they satisfy physics. And so the takeaway of this project, again, we train a scoring function to rank the contact states, and then we train a grasp predictor to complete a grasp given the thumb and the index finger contacts. And then we use the contact mode to guide how to navigate this pre-grasp planning process. And then we finally synthesize hand motion with collision and reachability, basically solving kinematics. And then, so the third task I'll talk about is extrinsic manipulation. What is extrinsic manipulation? It's manipulating an object using environment contacts. This is a very versatile mode of interaction. And recall, like in the pre-grasp case, we actually do sometimes do this with the dexterous hand. And it's very challenging because, again, this also has a lot of many different contact configurations, are difficult to plan, and there's a lot of sim to real challenge because we don't know the say, friction coefficient and whatnot. And so our insight here is we can take a divide and conquer approach. In particular, we claim that extrinsic manipulation can be broken down into primitives based on the contact configuration. So here we show like two primitives where the robot contacts the object and pushes it, and then pivoting it as the second one. And then within the same contact configuration, we can reasonably train a policy that is robust. So with reinforcement learning, standard tools. But the problem is, how do we, now that we have, let's say, a primitive policy for each of the contact configurations, how do we stitch them together? Because there are different contact requirements for doing different things. We can't pivot an object if it's not in contact with anything else. And so this project builds a framework using physical models to enforce these constraints. And so as an overview, we built a primitive library, define contact requirements, like say robot object and object environment contact. We take a demonstration, and then we can remap this task to different scenes and different objects by retargeting the contact configuration. And so we define these four primitives: pushing, pulling, pivoting, and grasping, with a mixture of classical control tools and learning-based tools. Each of them stay within the same contact configuration. And then we come up with a way to describe contacts, in particular, the environment object contacts and the robot object contacts. And then robot is assumed to be able to move freely between contact transitions. And then we take one demonstration from the human to fix the sequence of primitives we try to use. So this is very efficient, just one demonstration, and it doesn't even have to be on the robot. We label the primitives that are used during the demo collection. So in this case, we push it, and then we pivot the object. And then we run the contact retargeting framework that we built based on kinematic and contact mode constraints. So we map over the object state, solve an inverse kinematics to make sure the state satisfy the contact requirements for that specific object shape and scene shape. And then now that we fixed the object, we move the robot to establish the desired robot object contact. And then we're able to execute this task on a variety of scenes. So here we show the one demonstration being transferred to various different objects of very different shapes and sizes and a different environment. And so we can achieve long horizon tasks, I say, including up to 4 different contact configurations with the same primitives. That we prepare one set of primitives, but then by mapping the contact configuration, we are able to. Is this not playing? Right, yeah. So by mapping the contact configuration, we're able to achieve the same task on a variety of different objects. Yeah. So in the interest of time, I think I'll fast forward this part. And so the takeaway for this project is we can build a divide and conquer framework based on contact constraints using physical models, and then we can learn we can train goal-conditioned motion primitives with standard learning tools. And then we stitch these together with our physics-based constraint and achieve long horizon tasks that are otherwise impossible. And so in this talk, I've covered 3 tasks: dexterous grasping, dexterous pregrasping, and extrinsic manipulation. And so all of them use the analytical methods to make the computation more efficient, moving expensive computation offline, and then ensuring that the learning methods satisfy physical constraints at all time. And so with that, I would like to go back to the 3 questions I asked at the start of the talk. What is missing in robotic manipulation? Generalizability and robustness. The policies we have nowadays are mostly fragile. And what causes this deficiency? Is that there are a lot of complicated physical constraints in manipulation. And how can we use physical models to solve this? And we can do it by synthetic dataset generation, robust constraint satisfaction, composability, and multitask generalization, as shown in the 3 examples I gave. And so I would like to thank my wonderful collaborators for making these projects possible. And that's the conclusion of my talk, and I'm happy to take questions.
While the others were grabbing?
Yeah, so the question, I'll just repeat the question. And the question is, why does one finger stick out in the dexterous grasping project? And the reason that for that particular one, we only consider 3-finger contact, which is the minimum needed. So the 4th finger is just kind of sitting there. But eventually, the same math works for more fingers as well.
Kind of a related question. So in the pre-grasp, you said you require 2 fingers. But it seemed like what you're doing is reaching in with 1 finger, like to pull out the book. Why 2 fingers?
Yeah, so the question is, in the pre-grasp project, it seems like why 2 fingers? Right? Like in the book case, we only have 1 finger, and the answer is that we need at most 2. And basically, the thought process is that we would take 2 fingers plus the environment, so that's 3 points of contact, which forms a rigid caging. But then, of course, if it was a patch contact on the environment, like the book, then we really only need 1 finger. Any other questions?
So about your first project, when you do the dexterous grasping generation, looks like your pipeline started with offline learn grasp generator. Then you have a kind of a model-based optimization procedure to kind of refine grasp notation. Right? Sounds like it means for any given new graph, you do need to have a shape or some kind of model of the object to run your optimization, right? If that is the case, how can you run the whole process without the learning part? Can you also do a model-based grasping point generation? And how does your answer compare with that? I'm not sure if I got the last part. I'm basically saying that the information available to your method also supports a purely learning-free approach. You can, since you have the model for every single grasp, technically you can run a more traditional grasp point generator too. Right? Have you compare your method with a more traditional approach?
Okay, yeah, so to repeat the question, is the question is, we basically have full information, and so why don't we just run a learning-free method to directly generate the grasp? And so that goes back to the question of the global optimization, because it's very hard to come up with this full 22 degree of freedom solution if we start off from scratch. And so what the learning give us is essentially a good initial guess. And then so the learning also can see the initial guess differently, so that we get diverse grasp configuration even for the same observation.
Cool. And so you're basically saying randomly sample good grasp for 22 degree freedom pan is very hard. Right. Yeah, that makes sense. Pre-grasp problem, I don't know, I was thinking about this and thinking, the hard part is not so much to choose the initial context state, but rather the motion planning that is required to get the object into a state such that you can then grasp it. Is that correct? So that's as much a sort of accessibility problem as it is a contact problem.
Yes, so the question is the motion planning part should be, why is the motion planning part in the pre-graph problem not the hard part, as opposed to the initial contact state selection? So I think the short answer is yes, and that's why it is a very computationally expensive thing to evaluate, because we select the pre-graph, we have to go through the whole motion planning process to decide, hey, if it's good or not. But then that's why we learn a score function, because now we see the pre-graph state and we can have a guess, kind of a guess of how good this will be without having to solve the full motion planning problem. And we solve the motion planning problem offline.
So one more. So it's actually really cool to see it, doing the planning and work and picking things up, and then you get to a good result that's 87% successful. And then I think, well, if you actually want to use this in the real world, 87% successful isn't nearly enough. So can you give us some insights into where it's failing and what's going to be the next step to make it even better?
Yeah, so the question is, the 87% success rate we see is not enough for deployment, and what can we do about it? And so I think a lot of this actually boils down to engineering challenges, say the hand overheats and then it'll break, or we didn't bother coding up collision constraints with the table, so the hand might jam its pinky into the table and whatnot. And so I think I believe people call this the last mile problem, because going from 0 to 90% is it's just about as hard as going from 90 to 95. And so I think in general, it's just a lot more engineering work. And the second 90%. Yeah. But yeah, so there are ways, but I think it's less principled in a sense.